Do you know how municipal solar street lights pass on-site illuminance acceptance tests? Today, let's learn about the acceptance testing methods for illuminance uniformity and glare. Illuminance. When solar street lights turn on at night, the amount of light received per unit area on the illuminated surface represents illuminance, indicating how much light reaches that point. We typically measure this using a lux meter. During on-site acceptance testing of illuminance, we need to prepare a calibration illuminance design report and a steel tape measure or laser rangefinder for distance measurement. The lux meter measures the illuminance, and paper and pen are used to record the data. During measurements, we typically use the report-based point location method and the center point method. When locating points using the design report, we first open it. In this report, you can see the annotated points and target values. These correspond to the illuminance measurement points and verification data we need to locate on site. For single-sided lighting arrangements, the entire grid can be offset toward the lighting side. For double-sided arrangements, the grid points should be symmetrically positioned about the road center line. Once these points are found, use the lux meter, turn it on, place it level on the spot, record the reading, and compare it to the design report to verify. At this point, you might wonder, what if the road I'm measuring already has traffic, or if my road isn't an ideal rectangle? How should I measure then? Actually, a more practical method is the center point method. Divide the road area between two lighting poles into equal grids. The grid layout must follow these standards. Select a road section with length A and width B. The center of each grid serves as the measuring point. When at 2.5 meters, the maximum spacing between measuring points is 0.5 m. When 2.5 is 6 meters, the maximum spacing between measuring points is 1 m. When 6 of 15 meters, the maximum spacing between measuring points is 2 m. When 15 of 50 meters, the maximum spacing between measuring points is 5 m. When at 50 meters, the maximum spacing between measuring points is 10 meters. Record the illuminance value at each point. After carefully recording all values, calculate the next value. To find illuminance uniformity, use this formula: E equals E1 plus E2 plus E3 plus NN. Here, E1 and N are the illuminance values at each point, and N is the total number of points. Identify the minimum illuminance. Then, using the formula, uniformity equals minimum illuminance average illuminance, we calculate the illuminance uniformity, a measure showing how consistent the lighting is across the area. Finally, it is important to note that the primary cause of glare is luminance entering the eye that significantly exceeds the eye's adaptation range. Incorrect installation can cause direct glare. Glare typically originates within the LED lens, where multiple reflections of intense light reduce visual contrast, resulting in a washed-out appearance and a halo effect that can cause dizziness when driving at night. Therefore, proper installation is crucial. On-site glare assessment typically employs engineering methods, primarily by checking whether the lamp installation angle conforms to the design, whether the pole height is uniform, whether the beam directly enters the line of sight, and whether the lamp's optical components are correctly installed. If you're planning or evaluating the illumination of a solar street lighting project, I hope this video was helpful. See you next time!